The purpose of this video is to go over 3.3, more specifically the inverse of the function. So the beginning of the book, or the beginning of this chapter, talks about how to find the derivative of an inverse. And the first example just tells you how to find the derivative of the inverse at a given point, going through switching the role of x and y, because that's what a derivative does, right? If I have the value of the function, if I know the value of the function at one point, if I know the output, if I plug in the output to the inverse function, I get my original input. So we come up with this formula that we can use to find the value or the derivative of the inverse at a given point. So your book goes through this and comes up with an alternate version that makes a little bit more sense when we're not looking at points, when we're looking at actual functions. So we can take this formula and use implicit differentiation on the equation y equals the inverse function. So what they say is they let y equal the inverse function, and then they say x is a function of y, which is the first thing we kind of do when we have the algebra. Usually we have y as a function of x, right? And we switch the role of x and y. We have x as a function of y, and then we solve for y, and we have y is f inverse of x, right? So we're going to kind of go along the same lines when we went to find the inverse of the function, but now what we're going to do for the calculus part is we're going to let x equal f of y, right? So taking this, if I switch the role of x and y in my original kind of expression, and then I differentiate it, I take the derivative with respect to x. On the left-hand side, I get 1. And on the right-hand side, this is a chain rule. I take the derivative of the outside, evaluate it at the inside, times the derivative of the inside. Now, if you notice, I said y was the inverse. So dy over dx is going to be the derivative of the inverse, right? And it gets a little crazy here since I had the inverse in the superscript. I kind of want to write it like this, right? So if I find dy over dx, I found the derivative of the inverse, which is dy over dx here. So if I solve for dy over dx, I have dy over dx is 1 divided by the derivative of the original function evaluated at y, but y is the inverse, right? So a couple different ways to write that. Your book writes it as dx over dy, right? They write the derivative, they write y here. Since I'm taking the original function and I'm taking the derivative, I'm plugging in y. So y is, repeating this here, y is the inverse function. Now, it's not always possible to find the inverse, but we can kind of make it a placeholder. And that's what we're doing on Wiley here. So this was some student submitted this problem, and it didn't work out. Now, on this problem, you can find the derivative implicitly, right? We could say y is 2 over x plus 7. X is 2 over y plus 7. This is the process of finding the derivative or the inverse function. So I have x times y plus 7 equals 2. Xy plus x7 equals 2. I'm going to write that as 7x, so it makes a little more sense. 7x. Xy equals 2 minus 7x. Divide through both sides by x, and I get 2 minus 7x over x. This is the inverse function. And of course, I could write that as 2 over x minus 7. So if I differentiate this, I take the derivative with respect to x, I get minus 2x to the minus 2. And I could write that as minus 2 over x squared. So this is the derivative of the inverse using finding the inverse. But it's not always possible to do, so we can use this formula here. And this formula says I take the derivative of the original function, but I plug in the inverse function. So here I'm assuming that I can find the inverse, and again, the inverse is this function here. So this process is a little quirky because if I could find the inverse function, I can just take the derivative of the inverse straightforward. But you can also go through it the other way, which will make more sense, where if I find f inverse of x and I take the derivative, that's going to be 1 over dx over dy. And I'm going to show you that method as well. So I have 1 over the derivative of this function, but everywhere I have x, I'm going to replace that with a y. So what is the derivative of this function? The derivative of the top is 0, minus the derivative of the bottom, which is 1, hold the top, which is 2, over x plus 7 squared. So this is saying I take the derivative of this function, but everywhere I have an x, I plug in the inverse function. So I have to know the inverse function and plug it in here. So I have minus 2 over 2 minus 7x over x plus 7 squared. So this is algebraically really ugly and messy, but we can't be too afraid of algebra here. So I flip and multiply. So I have, find a common denominator here. I would have 2 minus 7x plus 7x over x. So that gives me 1 over minus 2 divided by 2 over x. Oh, I lost the squared. I can't do that. Sorry. So if I find a common denominator, the minus 7x and plus 7x, I have 1 over minus 2 over 2 over x quantity squared. So I have 1 over minus 2, flip and multiply. Oh, this is in the denominator. I gotta fix that first. This is actually the denominator here. So simplifying this, I have 1 over minus 2. This would be 4 over x squared. So this would be x squared here. Then this minus 2 comes down here. And I get minus 2 over x squared. So the algebra is ugly, but we can go through, find the inverse of the function. We could also take the derivative of the function and just replace let's look at this example. Very similar, we can take the derivative of the function and evaluate it at the inverse. Or we can go through the process. And that's exactly, the process is finding the inverse. So we want to find f inverse of x. So to do that, I have y is 8 over x plus 8. Switch the role of x and y. Solve for y. So I get y is 8 minus 8x over x, which is 8 over x minus 8. So this is the inverse function. This is f inverse of x. So I can find the derivative of f inverse of x by differentiating this function, which is minus 8x squared. Or I could use the formula, and the formula is saying I take the derivative of the function and plug in the inverse function, and the inverse function is what I found here. So what is the derivative of f inverse of f of x? Derivative of the top, which is 0, minus the derivative of the bottom, hold the top over the bottom squared, right? Again, this is the inverse function. So if I want to use the formula, I have 1 over the derivative of the function, but evaluated at the inverse. So the derivative of the function, minus 8 over x minus 8 plus 8 all to the second power. So I had to simplify the denominator first. It's going to be very similar to last time. I have minus 8 over, I need a common denominator, so I have multiply top and bottom by x, and then these two terms are going to cancel, and I'm going to be left with 8 over x quantity squared. Go ahead and write it like this. So simplifying the denominator, I flip and multiply, so I have 1 over minus 8x squared over 8 squared. So this becomes just minus x squared. So this is, the squared goes away, so if I cancel that, flip and multiply, I end up with the exact same answer as I would get by taking the derivative of the inverse function. So anytime you can find the inverse function, you can just differentiate straight from there, or you can use this formula. And another example, I don't know if I pulled up another example. Oh, here on number 9, again, very similar. They say you take the derivative of the function named x at y. So here, I couldn't find the inverse function this way. It's impossible. So what I can just say is I can let f of y equal 3y to the 5th plus 3y, not 3, sorry, y cubed plus 5. I can differentiate this with respect to y. F inverse of y would be 15y to the 4th plus 3y squared. Then I can just plug that into the denominator. So dy over dx is 1 over 15y to the 4th plus 3y squared. So this is a little weird because I have y's in here. It's because it's impossible to find the inverse of this function. So I can find the derivative of the inverse by doing this little trick here. Really, it's switching the roles of x and y. So if I plugged in a point, I have to be very careful, and that's what they're doing here on the book. Go back to the book here. They're saying if I want to find the derivative of the inverse at 1, I'm actually plugging in the output at 1, right? So if I plug in 2 to the function, I get out 1. So if I plug 1 in the inverse, I get out 2. So this is the output of the inverse function. So the formula would say, what is f inverse at 1? Well, f inverse of 1 is 2, so I plug 2 into the original function. So hopefully this didn't confuse you anymore. This is a tricky concept because it really relies on a lot of algebra, of understanding what it really means to be the inverse function, but more so we're talking about finding the derivative of an inverse of a function we don't even know what it is. It's just a placeholder to saying we're calling it the output of the original function. So to find the derivative of the inverse function, I don't have to find the inverse function. I can just plug in the output of the original function into this formula, and it's going to give me the value of the derivative at the original input location, right? So here, the picture again is a little helpful. I'm finding the value of the derivative at x equals 1. I'm finding the value of the inverse of the derivative at x equals 1, but I know the point of the function at 2 because the output is 1. So if I know the original point is 2, 1, I can find the value of the derivative of the inverse function at the point x equals 1. So this gets a little tricky, and I really don't like the way they show this here, because they have f of x and f inverse of x, and generally we see it as y is f of x and x is f of y. But for the purpose of the calculus, they leave it like this because they want your answer to be as a function of x. So if we know the slope here, the slope at x equals 2, to find the slope here, it's 1 over the value of the derivative at 2, right? So if I know this slope, I can find this slope. 1 over the value of the derivative of the function evaluated at x equals 2. So if I find the slope here, I would have 1 over that value. Again, hopefully this didn't confuse you anymore, if it makes sense. Looking at some of the examples, this example, it's impossible to find the inverse function straightforward. So I can find the derivative, the formula for the derivative. What I'm going to do using, kind of implicit differentiation here is if I took the derivative of this function, then I'm going to use the formula that is given that the derivative of the inverse, right? The derivative and the inverse of the function is 1 over the derivative of y with respect to, or derivative of x with respect to y. Derivative of x with respect to y. So switch the role of x and y, and then differentiate that, and then 1 over the derivative of that is the derivative of dy over dx, which would be the inverse, right? If we let that happen. So going through, solving, we get that. And here they kind of elaborate, we cannot solve for this expression directly, so we leave the answer in terms of y. You got to be really careful when we're looking at plugging in a point. If I want to find, okay, what's the value of the inverse function, the derivative of the inverse at 1, I actually have to plug 1 into the original function. That's what they do here. They plug 1 into the original function. So I'm really evaluating this at y equals 0. Right? If I plug 1 into the original function, I'm solving for what value of x gives me 1. So I have to be careful because this is here. What value of x would give me 1, or what value of y would give me 1, right? So if x is 1, then what does y need to be, right? Here, they have x equals y to the 5th plus y plus 1. So if x is 1, what is y? Well, y would need to be 0. So that's what I'm plugging into that derivative of the inverse. So hopefully that kind of helps explain what's going on in those two cases. You can always differentiate implicitly by switching the role of x and y, or just setting x equals the function of y, find the derivative, and then find dy over dx. And that's what they're doing here. They're letting y equal the inverse function, then finding dy over dx. So if they find the derivative of y, they found the derivative of the inverse. It just gets a little tricky when you have to go in and plug in a point, an x point, plug in x equals 1. Really, you need to solve for what value of y satisfies x equals 1 and plug that in to your formula. If you have any questions over this, let me know.